Welcome back to The Explainer. Today we're diving into a genuinely mind-bending discovery fresh from the journal Nature. We're talking about a breakthrough that completely resolves a major physics paradox. You see, it proves that the strange, hyper-probabilistic world of quantum mechanics doesn't just apply to single, isolated atoms. It can actually govern solid, macroscopic chunks of metal. It's a resolution that absolutely shatters how we define the state of physical matter, pushing the boundaries of what we even thought was physically possible.
So let's tackle a question that honestly seems to break the rules of classical physics. Can macroscopic objects exist in a quantum state? Up until very recently, the rapid decoherence of large objects made this seem basically impossible in everyday conditions. I mean, think about it. The physical world we interact with is highly predictable, right? A solid object has a fixed location. It doesn't just blur into some hazy cloud of probabilities, and it certainly doesn't exist in two places at once. So asking if macroscopic objects can live in a quantum state, well, that's historically been met with a firm no way by common sense and classical physics alike.
We've basically historically accepted this really strict dividing line in physics. On one hand, you have classical mechanics governing the macroscopic world, giving us definitive positions and completely predictable solid states. It's exactly why big objects behave the way we expect them to. But on the other hand, you've got quantum mechanics dictating the subatomic world, which is all about superposition and wave-particle duality. Down in that realm, particles take on these weird wave-like properties and occupy multiple states simultaneously. For the longest time, we've just treated these as two entirely separate realities with this hard, impenetrable boundary right between them. But guess what? A joint team of brilliant researchers from the University of Vienna and the University of Duisburg-Essen has literally just shattered that boundary. They ran an experiment that essentially proves quantum mechanics applies in domains where we assumed it simply couldn't survive. They took something that, by all classical accounts, should strictly follow the predictable rules of macroscopic physics, and they successfully forced it to play by the incredibly weird probabilistic rules of the quantum realm.
Now, the truly mind-bending part of this whole experiment is the scale. 8 nanometers. Now, okay, to us humans, an 8 nanometer diameter sounds unimaginably tiny. But in the highly sensitive realm of quantum physics, using metallic sodium nanoparticles of this exact size makes them absolute giants. They are definitively macroscopic. Getting an object of this sheer size to maintain a quantum state without immediately collapsing right back into classical reality is, frankly, an enormous physical feat.
Because, keep in mind, we aren't just talking about isolating a single atom here. That's been standard practice in labs for decades. We're talking about objects composed of solid metallic sodium that contain thousands of individual tightly bound atoms. Yet somehow, the researchers were able to force these massive clusters to act collectively in a singular wave-like state. Imagine a solid, multi-thousand atom piece of metal suddenly behaving entirely like a rippling, delocalized quantum wave. It's wild.
Now you're probably wondering, what kind of machinery makes this seemingly impossible physics a reality? Well, to pull off an experimental feat of this magnitude, you obviously can't rely on standard lab equipment. You need a highly specialized environment designed to completely isolate these metallic clusters from the chaotic decoherence of the outside world, completely shielding them from even the slightest disruption.
Enter the muscle device at the University of Vienna. This glowing vacuum apparatus is the exact experimental chamber where these massive, multi-thousand atom nanoparticles were forced into their quantum state. The environment inside has to be flawlessly controlled. We're talking a near-perfect vacuum. It's specifically engineered so that those incredibly delicate quantum properties aren't immediately collapsed by stray thermal radiation, random gas molecules, or literally any external vibrations.
So, let's break down exactly what happens inside that chamber. First, the macroscopic metallic nanoparticle is fired into the device. Then it encounters a gauntlet of 3 highly precise laser diffraction gratings, which effectively act as a Talbot-Lowe interferometer. And this is where the magic happens. Instead of passing through a single slit like a solid projectile, the particle travels multiple paths simultaneously, acting as a delocalized wave. Finally, because it traverses multiple paths at once, it creates incredibly clear interference fringes on the detector. And those fringes, they match standard quantum theory perfectly. To truly grasp what those wave-like interference patterns actually mean for a solid, thousands of atoms thick piece of metal, we kind of need to bring in a familiar, mind-bending analogy. Because seeing a macroscopic chunk of metal act like a delocalized wave isn't just some neat laboratory trick. It implies something totally foundational about reality itself and how matter exists in space. We're all familiar with the famous Schrödinger's cat thought experiment, right? Well, here, the paradox is actually realized in the lab. Each of these massive sodium objects was placed in a true quantum superposition. The metal literally existed in several places simultaneously as it passed through the lasers. It wasn't an illusion, it wasn't a trick of the light. And what's absolutely crucial here is that these results confirm that standard quantum mechanics does scale up, requiring absolutely no alternative physics models to explain it away.
To really spotlight the sheer scale of this achievement, consider the number 15.5. In physics, this is known as the macroscopic value, or mu, which basically quantifies the macroscopicness of a quantum superposition. Achieving a mu of 15.5 during this experiment is a massive leap. It's literally 10 times larger than any quantum interference experiment previously recorded in history. The team didn't just inch the boundary forward, they leaped over it by a massive factor.
Okay, zooming back out to our everyday world for a second. Theoretical physics and laser interferometry are undeniably cool, but why does forcing macroscopic metal into a wave-like superposition actually matter for us? What's the real-world application here, and where is this scientific breakthrough actually leading us in the years and decades to come?
Well, the implications are absolutely massive. First off, it definitively proves that the quantum realm extends much further into our macroscopic world than previously theorized. Second, it completely opens the door to testing even larger objects, really pushing the limit to see exactly where, or even if, quantum effects finally collapse into everyday classical reality. And third, it unlocks entirely new potential for advanced nanotechnology, paving the way for systems that leverage these bizarre properties on a usable, physical scale.
The source material even hints at these massive, quantum-behaving clusters acting as highly promising materials for the future, calling them essentially giant superatoms. So I'll leave you with this provocative thought. Could these exact, mind-bending metallic states provide the stable, macroscopic physical foundation required to finally power the world-changing quantum computers of tomorrow? The rigid barrier between the quantum and the classical is officially breaking down. Thanks for joining me on this explainer, and keep questioning the world around you.